Hello, welcome everybody. We're going to talk about microservices and Kubernetes. So if you're not here to hear about microservices and Kubernetes, you may want to go to the other room. Just last check. My name is Alain Regnier. I'm a technical architect and entrepreneur. I spent 10 years in Silicon Valley working for startups, for big companies. I'm a GDE, Google Developer Expert on the cloud, and I'm the co-founder of the GDG Paris and GDG Cloud Paris. Who knows what GDGs are? Okay, GDGs are just meetups for people using Google technologies, and GDG Cloud with a special focus on Google Cloud. What I do for a living, I do consulting services around Kubernetes and Google Cloud mainly. Both the setup of Kubernetes cluster, but also the migration to Kubernetes. We help companies to actually move to Kubernetes, and we also do training. A few words first. Who is using Docker already? Okay. Who's using Kubernetes? Okay. Who's running Docker in production without Kubernetes? Don't be shy. Okay, okay. So since most of you already know about containers, I'm going to go a bit fast on that part of the presentation. I've had experience where people didn't really know about it, so I had to spend time on it. We have a lot of things to cover, so I won't spend too much time on it. But basically, with the containers revolution, we moved from servers to virtual machines and then to the virtualization of the execution environment for payloads using thin containers on top of the container engine. Containers in our mind is usually something like that, the type of containers we put on a boat. And it's a pretty good image of what we really do with software containers. So I won't go in details about that. A few interesting things. Containers are not really new. If you really look in history, BSD jails in 2000, Solaris containers and zones in 2004, Linux containers in 2008. So that's much before you started hearing about Docker. It's based on two key technologies, C groups and namespaces. The usage of containers has been greatly simplified thanks to a company called Docker. What is Docker? Docker originally was a company named .cloud with a path solution with a custom container engine written in Python. Originally, it's a French company. It's now based in San Francisco. In 2012, they rewrote their whole engine in Go. I guess everybody knows about the Go programming language. And the first public release was in 2013. And within a few months, there was a big adoption in the community for Docker. And the key reason was that it simplified the use of containers. As a side note, the company raised a lot of money, more than $120 million over a 12-month period, which is pretty big, actually. Now, why use containers? Faster startup than VMs, smaller images, better performances. I think you all know about that. One thing that I really like is the improved modularity, where you can compose your application with smaller components that will talk to each other, and we'll get back to that as far as microservices are concerned. And also you can isolate technical inheritance in various containers to avoid all the issues we had before when you have several versions of the same application or with a different library version, for example. Now, when we have a lot of containers, we put them on a boat, but sometimes shit happens. And this is what you can get. So for that, we need a solution to manage and orchestrate all those containers. I would say that the winning solution in the orchestration war is Kubernetes. It's an open source solution that was created by Google, has been developed with partners including Red Hat, CoreOS, IBM, Microsoft, Huawei, and that is now under the supervision of the CNCF, the Cloud Native Computing Foundation. If you don't know about CNCF, I invite you to look it up online. There are a lot of interesting projects there, and it's very important for the future of Kubernetes. Basically, you can create, update, organize, and the goal is to define the target system and let Kubernetes maintain it for you. A few words on Google and containers. Google has been using containers internally since 2004. So when you go back to the history and think about Docker, you can see that Google was using containers way before Docker appeared. In 2016, Google was starting 4 billion containers per week. Let me say that again, 4 billion containers per week. So basically, they gained a lot of experience running containers. And they found out very early a lot of the pitfalls and issues you can get with containers. And why is it important? Because in the first open source Kubernetes version that Google released, they actually put a lot of best practice and a lot of solution to those problems they were having with containers. On a side note, they offer their own Kubernetes service called JKE, which is a Google Kubernetes engine. There are others like AKS. The point is that you can run your own cluster, or you can just rely on a cloud provider to run the Kubernetes cluster for you, and then you simply put your payload on it. Most of the time when you get started with Kubernetes, it's easier to start with such an offer. So JKE, AKS from Azure, etc. A few more details. You can run Kubernetes locally, on the cloud, on physical machines, or on those Kubernetes as a service offer. It's written in Go. It's based on a REST API, so it's very important because you can actually write your own application that will talk to the API and leverage all the features behind it. The resources are usually described in YAML file, so if you don't like YAML, sorry, you'll have to suffer a bit of pain. But we get used to it, don't worry. And we use a small command line tool called kubectl, which is equivalent to the Docker command line tool that you may have been using with Docker. And again, the goal is to manage application directly instead of managing the virtual machine or the computer behind it. Let's talk a bit about application. So the conference is about microservices. You'll have a lot of talks about microservices. I won't go deep. But basically, monolithic application, that's the traditional approach. All the logic is inside one big application. It's much easier to debug and to deploy because you have one big component. But it becomes problematic when the application starts to get larger. When you want to update the application, you have to update the whole package. In comparison, microservices, you have multiple small components talking to each other. They are developed independently. They can be developed with different languages and frameworks. They can be updated and deployed completely separately. And also they can be scaled separately, which is also a very nice thing that we'll see with Kubernetes. We only need to know the interfaces that we want to use to talk with the other components. And the developers can really focus on the business logic they have to work on without worrying about other parts of the system that they don't necessarily have the skills for. So basically more agility, flexibility, and speed. Also, it reduces risks because you can completely replace one of the components by a new implementation without impacting the rest of the system. Well, that's the theory. In practice, it's a bit more complex than that, but still. Let's talk a bit about some key Kubernetes resources. So I don't have time to go deep into what Kubernetes is and how it works, but I just want to illustrate a few of the resources we're going to use in the example. The first one is called a pod. A pod is a group of containers that are always deployed together. They're always started together, stopped together, replicated together. They share the same network IP and ports. And they can share data through what we call a shared volume. So the key thing here is that we're going to regroup several containers in one package, and that package will be our singleton, our simple element that we're going to replicate and move over the cluster. So I mentioned earlier that resources are described using YAML. You have an example right here. The key thing here is that in the specification, we put the name, the image that we want to use. For example, gcr.io, my project, image front, :2. And we specify a few additional parameters, and we can have several containers inside the pod. And to create a pod, we simply use the kubectl command with the create subcommand, and we specify the YAML file. And this is something that we do a lot in the Kubernetes world, using this kubectl command. As I said earlier, we could also be using the REST API directly. The next resource is called a deployment. So it's a special resource that describes the target we want to achieve. What it means is we have the pod templates, what will be in the pod, which containers, which image, which version. We have replication details, how we want them to be replicated, how many instances we want to have at the same time on the cluster. The update strategy, how we want to update from one version to another. One way to do that is using, for example, what we call rolling update, where let's say you have 3 instances of the pod. You're going to create a new instance with the new version of the software, and if it works fine, you're going to remove one of the old one. Then you're going to create a new one, and then you're going to remove one of the old one, and so on, until you've completely replaced all the pods. So this is an example of a deployment YAML file. The key thing here is that you specify the number of replica. Here it's 2. The strategy for update. Also, you specify selector and container images. We will see more about that later. The next resources that we're going to use is it's called a service. So basically, pods can be moved and recreated on the cluster. For example, if a container crash, if one of the nodes needs more resources, it can kill your pod and recreate it somewhere else. When it does that, you're going to lose the IP address of the pod. And of course, that can be problematic when you want to access that pod. Let's say you have an Apache web server in a container. It's running with a specific IP address. Then the pod is killed and restarted on a different node on the cluster. It will get a different IP address. So you're going to lose contact to that pod. So to avoid that issue, we use a service. Basically, it maintains access through a durable IP, even if the pods are replaced. We'll see a bit later how it works. The service targets pods that match the selector. So here we have an example. Yeah, we have an example of YAML for a service, and you can see the selector here, which is a key value pair. And basically, what it says is that this service will target all the pods that have this selector attached to them. Okay, so that's how we're going to identify which pod are associated to a given service. Again, we'll see that a bit more in details. So each service gets a specific IP address that is fixed. So as I said, if you kill a pod and you restart it somewhere else, it will get a different IP address. But a service will always keep its IP address. So once you've created it, you know that you're going to keep it. One nice thing about services also is that they can be resolved through environment variables or through DNS. So when you start dealing with microservices, one of the key things you want to do is called service discovery. Basically, you want to be able to find the services that you want to talk to, the other components that you have to talk to. And with Kubernetes, we get this flexibility of having DNS automatically updated for you based on the name of the service. We'll see in the example that this makes it very easy to do service discovery. There are different types of services. We won't go into too much detail. One nice thing also is to understand here, we have a port and a target port. The port will be where we will connect on the service, and the target port is where we will connect on the specified, on the matching pod for that service. So basically, for that service, I will connect to port 80. Then the service will forward the connection to one of the available pods that have the matching selector on its port 8888. So we can do a lot of mix and match based on that. Again, we'll see a bit more on the schema. Next one is called the Ingress. So an Ingress is a collection of rules that allows external connection to reach the services on the cluster. When you start running containers and pods on your cluster, they all get internal IP addresses that are internal to the cluster itself, but they are not accessible from the outside. So what you usually want to do is you want to set up a load balancer in front of those services, and that's exactly what the Ingress does for you. It provides a load balancer. It does SSL termination, so you can actually connect from the outside using HTTPS to the Ingress, and then all the connection inside are done using HTTP, which makes it easier to debug and investigate potential issues. Of course, you can use HTTPS inside also, but you don't need to. It also allows you to do virtual hosting. And when you are running on a cloud offer like AKS or JKE, usually you trust most of what's going on inside the cluster because it's hosted by a company that does security much better than you do. But what you want to be sure is that the connection is secure between the client and the Ingress, and that's what it does. It's using what's called an Ingress controller. So there are different types of Ingress controller. The most famous one are based on Nginx, the web server, or Traffic. But you can also be using the Ingress controller from your cloud provider. In the case of JKE, using the global load balancer from Google. And when there is no matching rules for what you've defined, the traffic is sent to what's something called the default backend that always return a 404 error. And it allows you to investigate what's going on. So here you have a simple example of an ingress. So the kind is ingress. And you can see here in the rules that we have one host called myserver1.mydomain.com. And when you get a request to that host name, basically it forwards the connection to the service name service1 on its port 80. So remember, we've defined a service with a selector, and we said all the pods that have this selector attached, which is like a decoration, if you want, for the pods, will be targets for that service. Now we're doing in front of the service with the ingress, we're saying all the requests to that specific URL will go to that service. And all the requests to that specific URL will go to that service, which is a different service. Again, I'll show you a big schema, and I hope that it will clarify things for everyone. Last two resources we're going to use are secrets and config maps. So basically, those objects allow to pass sensitive information for secrets or configuration settings for config map directly to the pod. They can be mounted as volume in the container at startup. So basically, when you configure the resource, you start your container. The container will have access in its file system to specific folder you will have created that will contain all the details on the config map or all the detail in the secret. We usually use secret for things like passwords and certificates. They can also be used as environment variable that you define in your YAML, and when the container starts, those variables will be defined by default with those values. One key thing also is that secrets are encrypted at rest in the configuration database of the cluster. So basically it means if someone steals a backup of one of the nodes, it won't have access to the secrets because they are encrypted when they are stored on disk. So here you have a simple example of a config map. Again, it's Kubernetes resources, so it's defined in a YAML file of type config map. And here we simply define two values, twiscore.db/IP with an IP address and twiscore.db user with a name. And then inside the deployment, we have a section called env, where we define environment variable. So here we define, the environment variable called db/IP, where we basically specify the value come from a config map kref, and the key is the value that was defined here. So from the persist config map. So basically, when this container will start, it will have a variable called db/IP that will contain the value that's here. It's particularly useful when you have different set of services or different versions and you want them to use different set of configuration. So it could be for your staging or pre-prod or development environment, or it could be when you use branches, like Git branches, and you want to have different installation on the same cluster with different settings. That's how we do it. Okay, let's talk a bit about a scenario. So it's a simple test application I've created called twiscore, which is a simple microservices-based application that calculates the score of a tweet. Who's on Twitter? Okay, I guess I'll talk to some of you. Basically, there are 4 key microservices in this application. The first one is called twiscore-persist, which it's responsible for persisting and retrieving data from the database. The second one is called twiscore scoring, which performs complex calculation, and complex is a big word in that case, to give you an evaluation, a grade basically for your tweet. Twiscore front, which is the front web application that can be accessed from the outside. And finally, the admin microservices, which give full access to the data and allow to do extra things. Only front and admin can be accessed from the internet. That's a key important thing. The other microservices are purely internal. So I'm not sure how you can read this schema. I will try to explain a bit. This represents the application. So if we start from the right here, here we have the deployment, sorry. This is the front deployment, which define 3 replicas. So we have 3 pods here. Each pod contains multiple containers. As I said, a pod can regroup multiple containers, and they have access to config map, secrets, and volumes. When we look at it globally, we can see the 4 services I've defined: the front service, the scoring service, the persist service, and the admin service. The front service is basically in front of the front deployment, and the way it works with Kubernetes is that we use what's called probes, and probes are similar to health checks that are being done regularly. So basically, it's like receiving a HTTP GET on a specific URL every few seconds, just to make sure it's working. This is usually what we do with load balancers to make sure the destination is alive. So if we go back to this example here, we have 3 different pods, and Kubernetes keeps keeps sending those probes to the pods to make sure they're working fine. If one of them crash, it's not working anymore. As I said earlier, the service has a selector attached to it, and it knows that it can forward request to any of the pod which has the same selector attached to it. But if one of them crashes, Kubernetes will detect that. And the way it works is that we have an underlying object called an endpoint, and the list of endpoints is actually the list of healthy pod that can receive requests. So if my pod here crashes, Kubernetes will detect it very quickly and will remove that pod from the list of endpoints. So any request coming to the front service will only be dispatched to the first and third pod here. Is that clear for everybody? Because this is a key part of how it works in Kubernetes. So, so again, let's say this one crashes. It's being removed from the list of endpoints associated to the service. Kubernetes will also realize that, hey, I've been asked to have a target of 3 replica for that pod, and I only have 2 healthy. So what Kubernetes will do, it will actually create a new instance of that pod somewhere else on the cluster, and will reinsert it in the endpoint list to be a correct destination. So it's very important because this is what we call the auto-healing aspect of Kubernetes, which is very interesting when we do microservices application. Your application can crash, you can have problem, it will automatically be healed. So that's for the front service. What we can see from the front service is that it's calling the scoring service. The scoring service is an internal service, and it's also calling the persist service here. Here we have the admin service, and we can see the admin service is calling the persist service. Now what's up front here is the ingress. Remember, ingress is a list of rules that allows to route requests from the outside. So basically, when we connect from the outside to this external IP, if we call something like /app, all the requests will be forwarded to front service. And if we call something like /admin, all the requests will be forwarded to the admin service. And then on the side here, we have the config map, secrets, and persistent volume we may use in our cluster. So again, this is just to give you an overall idea. So I'm using JKE for this example. Basically, the first thing we do is we create a work folder. We specify some configuration that's specific to JKE. You would do something similar on Azure. And then you just source the configuration. One nice thing that we use is the Cloud Shell, which is this section at the bottom where we basically, inside the browser, have access to a small VM from which we can work on Google Cloud. You have a similar one on Azure. Now, we're going to go through the example of the persist service, and then you just have to imagine that we do the same thing for all the other services. So first, we create a work folder, and then in that work folder, we create our application. I'm using a simple application in Python. I won't go in details. I will just show you a few parts. But basically, it's an application that runs a web server on a specific port. So I'm using this simple HTTP server in Python. I have a doGet method inside that class. What's important here is I define a few paths: persist tweets, retrieve top tweets, and retrieve all tweets that are mapped to a specific method. So anytime we call that pod running this application, I will handle those 3 calls. I won't go into detail here. It doesn't really matter. The thing is that we use we connect to the database. And we connected the database using certificates to secure the connection to the database. It's very important to have a secure connection to your DB. One last thing I do here is at the very beginning of the program, I grab the host name of the system, and I save in a variable the last 5 characters of the host name, because this will allow me to know in the logs I generate where the thing happened. If I don't do that, and if I have 3 instances of my pod, I won't know exactly which pod generated which log. Okay, so it's an interesting thing to do. Now, what I do, I'm just checking my database. I have a few information that I export. I'm starting my program here, the persist program. Then from the Cloud Shell, I will use something called Web Preview. I don't know if you're familiar with Web Preview, but basically, it allows to connect to that Cloud Shell VM remotely from your web browser. Only you can access it because you're logged in into your account. It's very efficient when you want to debug and test things remotely. I specify the port number here, which is 8086 in that case. And then I can simply do this request up there. And I get a message from my program. What's important here is that here I have the last 5 characters of the host name of the system. And when we start running with containers, the pods and the containers will get names that are semi-random, and again, that will help you know where it's being executed and who's handling your request. So if I do this call here where I pass a few parameters, I get a response tweet added. It was added to the database. And if I do retrieve top tweets, I get the example of the tweet I created with a score. So in this schema I've shown earlier, what happened is that the front actually called the scoring service with the value I gave it, received the value, then called the persist service to save it in database and retrieve the information. Okay, and we can see in the logs where I'm running the application what's going on. Now, we tested the application directly in the Cloud Shell. Now we want to move it completely to Kubernetes. So first we have to create a Docker file, a simple Docker file that executes the Python application. Then we build the container with a Docker build. Then we check the images. We can test the container locally by doing a Docker run and passing the correct parameter on the command line. Same thing, then we can use the web preview and access it. So we first tested with the program running on the command line in the Cloud Shell. Now we're testing by connecting to a container we've built. We can check the console to see what's going on. And we can also use curl on the command line to retrieve the value. Next thing is we're gonna tag this container we've created. So we're going to use gcr.io, which is the Google Container Registry. It's a bit like Docker Hub, if you want, when you're working with Google Cloud. And we're going to tag this image as version number 1. After I tag it, I can see, doing Docker image, that I have an image here that starts with gcr.io. And what it will help me do is I can then do a Docker push, specifying the full name, and it will push my image to the GCR registry on my project. It's a private registry, so I can do everything I want. Nobody can see it by default. Once I push the image, I can go to the Google Cloud interface, and I can see in the GCR view that I have a new image here, twiscore-persist version 1. It's in my registry. It's important to do that because then we will be able to reference it from our Kubernetes resources. Now we need to do the same things for the other containers that I mentioned, the admin, the front, etc. So let's assume we've done it. Now let's talk about Kubernetes itself. So far, we've created our application, we tested it locally, we created a container, we created an image for the container, we could push the image to the registry. Now we're going to create the Kubernetes resources that we've talked about earlier. First thing that we need to do, we need to create a cluster. So this is a quite complex command line, but basically what it does, it creates a Kubernetes cluster on JKE. And after a few minutes, we can do a get nodes, and we can see the 3 nodes from our cluster. Those are the virtual machine, or the physical machine, if you want, on which we're going to run our Kubernetes payload. Next thing we're going to do, we need to create a secret to contain the certificate we use to connect to the database. I mentioned earlier, all the connections to the database are being encrypted, but we need to have authorized certificates. So we're going to put them in a secret. When we do Kubernetes get secrets after that, we can see our secret here has been created. Next thing, we're going to create a config map for configuration settings. So this is the example I showed a bit earlier with the IP, the user. You should not put the password in the config map. You should put it in a secret, but I'm trying to do something simple here. I also do apply on the YAML file. Again, this is something we do a lot when we want to create resources on Kubernetes. And then if I do kubectl get config map, I can see the config map I just created. So learning to use kubectl is very important because we do it a lot when we do development, debugging, and so on. But the thing is, when you get to a more organized way of doing software development, you most likely want to use a CI/CD solution that will do most of that for you. The problem is when you rely too much on your CI/CD solution and you have a problem and it's not working as expected, you still need to get your hands dirty and use kubectl command. Next, we create the deployments. So still for the persist services, we mentioned it earlier. We have the image here that we built. We get the configuration from the config map. We specified only one replica for that. In that example, we could have several here. And finally, we mount the secret so that the application, the Python application, can access the database using the secure connection. Again, if we don't have the certificates, we won't be able to connect to the database. Then we, again, do apply, and this will create our deployment. When we create the deployment, keep in mind the deployment will create the pods for you. So if I say I want 3 replicas and I apply my deployment, I will get 3 pods, 3 instances of the pod that's defined in the deployment. In that case, I get one pod. One thing I can do is I can check the log of the pod by doing a kubectl logs here, by giving the name of the pod. Remember, I mentioned earlier that I'm using the 5 last character of the pod. I'm extracting it in the program. That's because this is what the name looks like. So I can check the logs here. One nice thing I can do to test, to verify everything worked fine, is actually I can connect to my pod. So I do that by doing an exec command on the pod itself, and I'm running sh. So when you build your container image, especially during development phase, you want to put a shell in your container so that you can connect interactively into the container to see what's going on. When you go to production, you don't want that. So you want your CI/CD chain to remove the shell, because if a hacker goes into your system and has access to a shell, he can do a lot of nasty things. If you don't put the shell, it will be more difficult for him. But during the development phase, you want to have a shell in your container. So it's as simple as doing a yum install bash, for example, in your Docker file. So here I'm connecting into the container, and I'm just checking what's in the config folder. And if you remember, here in the secret part of my deployment, I told it to mount my secret twiscore-db secret vol in the folder /config inside my container. So when I connect into my container and I go into config, I can see my 2 certificates in the live container. Again, those certificates are not in the container image. You don't want to have sensitive information in your container image. You want them to be attached at startup. There's a funny thing about that one on Docker Hub, where people were publishing container images on Docker Hub with their passwords inside the images. And so there are programs that are scanning all the time all the images on Docker Hub to try to find the various passwords. So don't put your password in your image, just attach them like that. One other thing I can execute when I'm inside my container here is just the env command and do a grep on dbip, and I can see that this variable has been created for me. It comes from the config map we've created, and it makes the value available in my application. So to test it, one nice way to test it is we can actually do a port forward. So this is a nice trick that not everybody knows, actually, where you can forward a port of your local system into the pod running inside the cluster. So but what I'm doing here is I'm saying forward my local port 8086 to the 8086 of the pod. I don't care where the pod is. I don't have to know. I don't have to know the IP address of the node on which it's running. I don't care. I'm using the kubectl command for that. And then from a second Cloud Shell, I can simply do a curl on my local port 8086, and basically I get a response. So I can verify it's working fine like that. I can check the logs again of my container, and I can see the details of the request I sent. Next thing, we're going to create a service. So the common type of service we use is called cluster IP type, and that's when you do Kubernetes on-premise or on most installation. But in the Kubernetes world, there are, like in every world, there are differences of implementation based on where you are. And when you run on JKE, you cannot use cluster IP service to be accessed by an ingress. Remember I said earlier, the ingress will forward routes to different services based on the path I've defined or based on the name of the system I've defined. So I have to use not port here. But be aware that most of the time we use cluster IP type. I won't go into details about that. We can discuss that later if you want, actually. So basically, I'm creating my service. It's a very simple service. I say expose port 8086 on the service and forward it to the port 8086 of the pods that have a label that match my selector here, which is app persist. I apply my service to create it. I can check my services. I can see there is new services created here. I can describe it to get more details, including its IP address. As I mentioned, it gets an IP address on the cluster that it will keep. And I can do a port forward to the service directly, exactly like I did with the pods. This will allow me to do a curl and verify it's working fine from the service. You have to do that for other microservices as well. We did it for Persist, but you have to do it for the other ones. Now let's see how we can update the code. Let's say we modify the source code of the front service. In that case, it's twiscore front. I just modify the code. What I do, I have to rebuild my container. I will tag it with version 2 instead of version 1 like earlier. And I will push the image to the registry. Next thing, I need to update my deployment to tell it, hey, don't use version 1 anymore, use version 2. So I only change this line here to say version 2. And I do apply, and it will do the update for me based on the strategy I defined in the deployment. If I do a get pods quickly when I've done that, I can see something interesting. I can see 3 front pods, because in my deployment, I said I wanted 3 replicas that are terminating. Actually, I only see, yeah, this one is still running because it's very early. But basically, I'm creating new ones and deleting the old ones. And after a while, I can see those 3 fronts are terminating, and those 3 are running with the new image, with the version 2. So that's how simple it is to update code of one microservices without affecting the rest. Last thing, the ingress. So I created a simple ingress. I created a name here that I attach to the IP address I will receive for the ingress. And basically, I say all the /app requests, send them to the front service, and all the /admin requests, send them to the admin service. Okay? And that's how we're going to access it from the outside. I do apply on my ingress. I can check my ingress. At this point, I don't have an IP address, so I have to wait a while. It may take a few minutes based on where you're running. After a while, you get an IP address. This is your official external IP address for the ingress. Now you can connect to that IP address and make your request. For example, I can do a curl, specify the host header that I've defined in my ingress, which could be fake. It doesn't have to be a real DNS entry, because since I specify it, it will be handled directly. And then I get a response. So if I do top, I first get a 404 error, so I may have to wait a few more minutes. But after a while, I start getting the real answer with my real data. One thing to notice is that if you do a path different than those that are defined in the application, for example, test doesn't exist on the front microservices, I get an error from my application where I'm returning unknown. I don't know what you want to do. But if I specify something wrong directly at the top, like /test, which is not defined in the ingress, I end up on this default backend I mentioned earlier. By default, you get a 404 error, and that's how you know there's something wrong in your configuration. A few more words. So if I test the URL directly, I get the default backend because I did not specify a path defined in my ingress. But if I do /app/top, I get the view of the tweets and the scores I've sent. I don't have much time left, so I'm going to go faster than that. Oh, yeah, one interesting thing here. If I do this request twice, here I can see that I've been served by the pod that finished by XFNB9, okay? And if I do a refresh, then I get the same answer, but this time by the pod that ends with P4KGR. Again, this is to show you that we really have a load balancer that's balancing the load over the different pods of the application. Okay, I can add tweets. I'm going to go a bit faster. And if I check the resources at the end, I have 3 different deployments, the front, the persist, the scoring. And I have 3 pods for front, 1 pod for persist, 2 pods for scoring. And I have a few services. This is the schema we've seen already. A few last words. So Microsoft and Kubernetes, we can have a basic approach to microservices using Kubernetes. Components are isolated thanks to containers. Service discovery, very easy with DNS. I didn't really show that, but basically the request I do to internal services, I simply do a HTTP call to the name of the service. One side note, you might want to use HTTPS instead of HTTP, especially when you come from the outside. When you are inside your cluster, it's not as needed. At least that's what I think. Kubernetes can restart automatically a crashed microservice. That's what we call it auto-healing. We can do updates very easily. Scaling can be done manually. I just have to update the number of replica in my deployment. If I change from 1 to 2 or 3, it will create the additional components for me. Or it can be done automatically using the horizontal pod autoscaler, where basically it look at the CPU usage and or some custom metrics to know if it needs to add more pods or to remove pods. And we can simulate environment with Kubernetes namespaces. Finally, with too many microservices, it's difficult to know which one is talking to which one. And so for that, there are new concept called service mesh, and Istio is one of the key ones that you may have several talks today about that. It makes it easier to understand what's happening and to control what's happening. But it's still fairly new. It uses a lot of resources. It's not completely dry as far as I'm concerned, but it's going in the right direction. That's it. So I'm done for the talk. Just a side note, for those who are interested, I'm doing a one-day training on Wednesday through the Box Microservices on that subject. If you're interested, come and see me, or go see Oxian and ask about that. It's on Wednesday, and we go much more in details into the whole concept here. Thank you. I can take questions on the side for those who want. Thank you.